question from a book example. And if you haven't been to Gapminder, I'm going to go over this again later in the class. These quizzes here are really fascinating. Welcome, Jorge. All right, so we want the data here. Then income, we've got income versus child mortality right there. And we want to get 1,800. Is that in the beginning?
The very beginning, 1799, but yeah, it's pretty close to the beginning.
And then which country, part B, has the largest income per person? And that is what we're measuring on this axis. So it looks like it's Iraq.
See?
They were thinking the Netherlands. Where's the
They're saying the Netherlands, and I'm like,
okay.
So it's not just me that's crazy,
no,
right?
Okay. I will write to them and say, hey, I think you have an error unless there's something we're missing. And I thought I found another error in the book yesterday, but I was wrong. Good reading, good eyes. And we'll look later in the class at how to make a simpler bubble chart than this one right here. All right. Thanks for that question. Yeah, and while we're in the book, I'm not going to go over this example because the book does such a good job of it, but be sure to check out not the spaghetti one, oh, that's cute. Discrimination among the developmentally disabled example. They give a few different graphs where they're trying to explore what's going on with this data about expenditures on people that need assistance due to some disability. And they do a good job of kind of walking through trying to figure out what's going on and why we need to look at multiple views of the data and multiple variables. So be sure to check that example out later. All right, so a little review of big ideas. Last time we'll play with a couple of data sets today. Whiteboard, please. Thank you, there we go. So mainly what we worked on last class were scatter plots and linear models. And that's mainly what we're going to work on today. Scatter plot, remember, is a graph of two quantitative variables where we treat the x and the y as related values. So plot of points for two related quantitative variables. Jacob. And we're interested in linear models. So anytime we have a data set with two quantitative variables, the first thing we're going to do is we're going to make a scatter plot and ask ourselves, is there a linear trend? And words we've used synonymously with trend were association or relationship. So it's important to look at that. Another thing I pointed out before that we need to consider when we look at that trend, are there any significant outliers? And we do have measures for outliers based on the IQR and the standard deviation that we could explore for any particular one of these variables. But usually we're just looking on the graph, is there a point that's just way off from the other points, and what should we do about it? And then 3, is the correlation reasonable? And remember, correlation is that we use the letter R for the correlation coefficient. Just summary of some stuff from last time, and we'll apply this. And the correlation coefficient is always going to be between 1 and -1. And when we're out on the fringes here, like toward 1, we say that's strong correlation. And toward -1, that's strong correlation. But near 0 in the middle of this interval, near 0 is weak. And it was asked last week, like, well, where's the cutoff for strong and weak? And the answer is it depends on the data set. There's no definite cutoff. We can't just say between -0.5 and 0.5, those are weak all the time. Sometimes they are, sometimes they're not. But we're just going to use that as a rough rule. If it's between -0.5 and 0.5, we're going to say, you know, I'm not that excited about it. But this isn't a definite rule in statistics. I just got to remind you of that. And chapter 9 goes into this further. So if we had more time or a second course here at BMCC, we would explore this further. All right, so those are the big ideas there. If we do have a scatter plot that has a linear trend, if the correlation coefficient is reasonable and there's no really big outliers, then we find the model. So what is a linear model? All right, so given that all of these things are okay, we proceed to find y equals mx plus b. All right, we want to know what's the slope of these two variables and what's the initial value here. And today we'll explore a little more is why is the slope important? Why is the initial value important? What do they mean to us? So let's look at a couple of examples on that. I'll share a data set with you. So when I'm well and I have some free time, I like to mountain bike. And so here from my bike computer are some numbers about my ride. Time in hours, those aren't minutes, it's just 1.11 hours. And then distance in miles, so almost 7 miles there. Let's let you guys play with this too if you wish. Make sure anyone with the link can view it. Thank you, Google. And if you check out the chat, you should find the link to this document. And if you wanted to play on your own instead of just watching me, remember you would have to make a copy of it in order to play it. So first thing I want to do when I get two quantitative variables like this is just say, okay, well, let's look at a scatter plot. Does there seem to be a linear trend? All right, so here they are. There's not many points, right? I only got a few of them. But it looks like as time goes by, the distance goes up. So yeah, I see a linear trend. Are there any outliers? Well, you know, this one I did seem to have gone for a longer ride than these other ones right here. But is it really an outlier? I don't think so. I'm going to say it's not too bad. So I'm looking at that and saying, okay, I think there's some linear trend here. So next thing I do is say, all right, I said this isn't really an outlier. I don't think. I'm going to go with it as not. So I'm going to go and find the correlation coefficient. So over here, I'm going to put in R. Under, I'm going to go equals correlation. And that's the one I want there. And it says grab your Y's, comma, grab your X's. So we did a bunch like this last class. So I have a correlation coefficient of 0.8, which is relatively close to 1. So that's reasonably strong. Reasonably strong correlation. So I'm just going to put a little note there. I'm moving along in my questions. So I'm going to find the slope and the y-intercept because I think this is roughly linear and That 1 point doesn't seem to be too bad of an outlier. And I didn't actually measure it, but I'm imagining a line going through those. To get the slope, we just use the slope command. And just like the correlation, it says, hey, what's the y? Where are the x's? And then the y-intercept, which is just intercept. Y's and x's. Now, just a note on this, for the y-intercept and the slope, you've got to get the order correct of the variables, y and then x. If you don't, you'll get the wrong numbers. The correlation coefficient is more forgiving. It is symmetric. It doesn't matter if you screw that up. So if you get them backwards for correlation, no big whoop, you get exactly the same number. If you get the y and x wrong for the slope and the y-intercept, you get the wrong numbers. So I'm just kind of imagining a line passing through here. And let's see, 0 isn't even on my graph, so I'm just going to tweak this a little bit just to imagine what's going on here before I edit. I'm trying to think about the slope of 7 and this y-intercept of about 1. Does that seem reasonable when I look at these points? So a couple things. I'm going to change the horizontal axis to get all the way over to 0. It's going to shift things over a little bit. Okay, so here's my points over here. And when I'm biking, I would expect that if I didn't spend any time biking, I haven't gone anywhere, so my line should go through the origin right here. However, my points don't perfectly line up, so that's probably not going to happen. Let's put the line in there. So to get the line in there, we go to series and say, show me a trend line, please. And I mentioned in class the other day that there are many ways variables can be related. There's all kinds of curves out there, and the spreadsheet program does offer many other options: exponential, polynomial, logarithmic, power series, and then moving average. So if I think there was a curve to the data, I could try a different trend line. And the power series, interestingly, came out to be pretty close to linear. Use a little bit different. And so notice when I trace this line down here, it comes close to the origin here, 0, 0, but it's a little bit tweaked upward, right? And that's that y-intercept of 1. Slope here, 7. So for every 1 unit I go horizontally, the graph is climbing up 7 units. What does that mean? We'll look at that in a sec. So I have my linear model here. I'm just going to write this down in my notes. Screenshot, data, graph, numbers. So here I have X is my time in hours, right? That's my X-axis right there. And my vertical axis I often call Y for lack of imagination, but sometimes we pick other letters for those. So those are my Y values. Does it make sense that this is X and that is Y, or should it be the other way around? Should the distance be here and the time there? Sometimes there's only one way it can go sensically. Otherwise, other times it can go either way. So the way I'm thinking about this one here is time goes by. I cannot stop it. I have no control over it. It's independent of me. So that's why I'm choosing time to be my independent variable. And then the time I spend biking dictates how far I've gone. So the distance is dependent on the time. So here I'm saying the y is my dependent variable and x is my independent. Right, time is independent, it just keeps going. Other terms we use for these is y is the response variable. And that response we get is explained by whatever x is doing. So it's explanatory. And could we switch those? Could it be the distance traveled dictates how much time we bike? And thinking about that, I'm like, well, yeah, I guess the farther I bike, it must take longer. So somebody could argue you could switch them, but I'm just going to stick with the idea that time is independent it's got to be the explanatory variable. It's a great one. Fueling source versus distance and time. Yeah, the longer I bike, right, I gotta pause to get some fuel there, and have a little snack, a couple bananas maybe, and a snack bar. But I can bike for 2 or 3 hours without needing a snack. But most of these rides are short. I think because the ones I grabbed here, I was mainly doing a lot of hill climbing. And so after climbing several big hills, I was like, okay, that's enough for today. And so I'm slow. I have these slow short rides going on. All right, so again, I think this should be the explanatory, and I think this should be the response variable. And my equation here then is y equals, if I go to 2 decimal places, actually since the data has 2 decimals, I should go 3 decimal places. Usually we go 1 more place than the data. So I would say my slope should be 7.089x plus 1.347. So this right here is my linear model. The equation is the linear model. All right, so what does this equation tell me? So let's think about the slope for a moment. What is slope? Slope is rise of a run. Well, what's my rise here? Well, my rise is a change in distance. So change in distance. And my run, right, going this way, that's a change in time from here to here. Change in time. And I have about 7, so I'm just going to round that to 7. My slope is 7. I need a rise and a run, so I'd have to write 7 over 1. Well, 7 what? Well, it's a change in distance. Distance is miles, so that'd be 7 miles. And time, 1 what? Well, 1 hour. And then what I want to do is I want to take this idea of 7 miles over 1 hour and just write a sentence to explain it to somebody else that's not into math and statistics. And the important part of that is that these are changes in distance and changes in hours. And we usually start with the explanatory variable when we write what slope means. So next thing I'm going to do is I'm going to interpret the slope, which just means write a sentence in common language. All right, so starting with the explanatory variable, that's a positive, so I would say something like increase or goes up. I used to use some words that mean positive, because that's a positive number there, positive change. So for an increase, lots of words to choose from for this, of 1 hour, Gary's bike ride, we expect an increase, because that's a positive number too, right? These are both positive, of 7 miles in distance e-bikes. And when we take all of these points and we condense them down into a line with a slope, that's basically an average. So then I usually add something like on average. That should be in there somewhere. That's not true for every bike ride, but that's the trend of the bike rides we have here. On average, he's going about 7 miles per hour when he bikes. So the slope, if we do see a reasonable linear trend to the data, is very meaningful, and we should be able to explain it by looking at what are the units of the 2 variables that are changing. And then we need to write a sentence that explains that change with those numbers. Y-intercept, let's take a look at that one next. How would we interpret that 1.34? I'm just going to call it 1 for simplicity here. So B, that's our y-intercept, is actually a point. It's the point 0b on the graph, right? That's this point right here. If x is 0, Y is about 1 is what I have right there. All right, so 0B. So in this case, though, it's about 0, 1. 0, those are hours. And 1, that would be miles. Now this one is not a change, it's an actual measurement for each. So if Gary bikes no hours, he should cover 1 mile. I don't know about that. Oops.
Maybe if it's a stationary bike.
Yeah, but this one's definitely a mountain bike. And that is definitely the point on the graph. So if Gary bikes 0 hours, then he travels. That's the interpretation of this based on what those variables mean, 1 mile. All right, so this is crap. This is not true. That can't be possible. So what's going on here? Well, although the slope is always going to have a meaningful interpretation, the y-intercept may or may not. If I were to say, well, that should really be a 0 there, not a 1, then what's going to happen, let's go to my graph paper to show this. Page, yeah. So if I were to regraph this with a y-intercept of 0, that means I would have to start here and go up. And the line shifted down and it doesn't fit the points as well. There's more points farther above the graph than below. And the point of the linear regression line, the blue one here, is to kind of split the difference in how far the points are above or below or near the line. So it minimizes the distances of these points from the line. This red line does not. It doesn't do as good a job. So although I have a y-intercept that doesn't have a meaningful interpretation, I need it to get the line in the right spot. So all I can say here is this, oops, back. This is not meaningful. But we need that number to put the line in the right spot. So sometimes when we try to explain what the y-intercept means, we find it doesn't really have a meaning. However, we just need it to make the right kind of predictions. So then what could I do with this line? Well, I can use this to make predictions about other rides. So I'm just going to do a couple more things here. Insert another column. Yeah, that works. So I'm going to do 2 things. I'm going to calculate the predicted values based on the equation. Predicted. And then I'm going to calculate these distances from the line to the points. So back here for a sec. Let's get rid of this red line. Ah, missed it. Oh, come on. There it is. So when the computer calculates the correlation coefficient, the slope, and the y-intercept, what it's doing is it's trying to find an m, a value of m and a value of b, so that these vertical distances from each point to the line, every single one of these vertical distances here is minimized. The way that's minimized is complicated, and we're not going to go over it. We're just going to accept it. But the short side is it's like calculating standard deviation. The line is like the average, the mean, and the deviation are these vertical lines. These deviations, in this case, are called residuals. Some of the residuals have positive values, like this one, and some of them have negative, right? Because it's below, negative, above, positive. So this is a positive residual there, that's a negative residual right there. If we were to just add up the residuals, we would get 0. They're going to 0 out because the line is the average, like we saw with standard deviation a while ago. So what they do is they square the residuals and add them up. And so what the linear regression line does is it finds a slope and a y-intercept that has the smallest possible squares of all of these lines added up. Any other line doesn't do the trick. Only this particular technique that gives us these numbers here and here. So to calculate those residuals, I need to know what the y value is on the line so I can subtract it from the y value on the data. So let's calculate those predicted y values. So the predicted y value just means use this slope and that y-intercept. I'm going to use rounded versions. So I'm going to say the slope is 7.089 to the nearest thousandth. I'm just going to type it because it's easier. Times, I have to click on the x value here. Plus the y-intercept, which I'm calling 1.347. Once I calculate the first one, I can fill them down. I could go with the automatic fill down. And if I were to graph these, what I would see is that point is, each point is just on the line, but above or below the given points here. Is what we find if we were to graph those two. So let's graph those for fun, just to prove it. Want a scatter plot. And the series should be, let's see, that goes, I want to see, I want the distance and predicted, and then here. So you can see that these points line up, and they're going to be on the trend line for the blue points. The red points are the trend line for the blue ones. So if I go to my series, and I just do the original distances, and add the trend line, you can see those red points just line up. They're the related point on the line to the given data point, and so on. So usually I don't graph them together like that. It's not necessary, but I did want to calculate these. We call these numbers the y-hats. And then if I want to calculate the residual, that vertical distance, I always take the actual value minus the predicted value. Oops, get that totally wrong, try it again, equals the actual data value minus the predicted data value. So these would be my residuals here. And I'm actually going to graph these residuals because usually when you look at the residual plot, that's like a fourth check to see if a linear model is okay. You want to see them scattered with no particular pattern. So if I graph the times versus the residuals, I'm hoping to see just this little chaotic graph. And so there's not supposed to be much of a pattern here. And I really should do a scatter plot. Oops. Come here. And who's doing this to me today? Time should be x, and series should be the residual. There we go. So again, this one's farther out from the others, but there's some above and there's some below, and I really don't see a pattern to how they're spread out here. If there is a pattern, then we would say, huh, maybe a linear model wasn't a good idea. I'm just going to show an example of that. Let's see, CO2 is a good one. So here I did it ahead of time. Give it a second to load. If you want to take a look at this on your own, future, here's the link. But this is just going to be a brief demo. I really don't need to get to the spreadsheet. So here's my CO2 data, and it kind of lines up, but I think I see a slight curvature to these. Notice that there's some above in the beginning. This one looks like it hits it almost, and then there's a bunch below, and then there's some above again. So this looks more curved than straight. And so I said, well, it's kind of straight, so let's just do it anyway. So I calculated R, M, and B, and then I found the predicted values here, the y-hats, and I did the subtraction to get the residuals. And so let's look at the graph of the residuals. is there a pattern to the graph of the residuals? And the answer is, well, yeah, there's a curve to these residuals. I see a pattern there, right? Compared to my mountain bike rides, they were just kind of scattered randomly. I don't see a pattern there, but there's definitely a pattern here. So this fourth thing says, pattern to the residuals means you shouldn't have used a line here. So this is a different kind of regression. It's not a linear regression. So we need to rethink this particular problem right here. And nonlinear regressions are covered in usually a second or third course in statistics. But the spreadsheet could do it for us if we ask nicely. So if we go to edits and then customize the series, instead of saying, give me a linear trend line, I could try something like a polynomial trend line. And now it's trying to fit that curve there. Now, a polynomial trend line is a little more complicated. You don't just have a slope and a y-intercept. And I'm not going to get into the details of that. So calculating y hat and the residual is a bit trickier. And again, that's covered in a second course if you find this stuff amazing, or you just have to take a second course. All right, let us look at another example. And actually, let's go back to this one for a sec. I'm going to put that line back in and then talk about the slope here. Series line. I have the numbers here, but we'll take a look at what those mean. Let's show it there. Let's fix these titles. That's CO2 parts per million. Screenshot. So we can talk about it. All right, so I have my two variables here. So X is just simply the year. And Y here is the average atmospheric CO2. And I had to look that up in the book to be sure what it meant. Average atmospheric CO2 in parts per million. And the slope here, M, is about 1.47. And I'm going to call it 1.47 over 1. And remind myself, this is a positive change there. That's a positive change there. This one right here is the CO2 parts per million. And this one right here is a year. So I want to interpret the slope here. What does it mean? Okay, so let's see. For each additional year that goes by, say, so I need to indicate this change, right? It's not just 1 year, it's an increase of 1 year because it's positive. So for each additional year that goes by, the atmospheric CO2 is increasing, right? That's a positive number up there, by 1.47 parts per million on average. Right, so I need to get in the change in X and the change in Y here, the change in my explanatory variable and the change in my response variable. And it's going uphill, so they're both positive. So for each additional year that goes by, atmospheric CO2 is increasing by 1.47 parts per million. Sometimes the Y value is, the Y-intercept is significant, sometimes it's not. So if I was also asked to interpret the Y-intercept here is the point 0, negative 2571. This is the actual year, right? So what is year 0? That was 2,000 years ago. 2,000 years ago, the atmospheric CO2 was negative. No, that's not possible. That's crazy. So there is no reasonable interpretation for this. But I need that to get the line in the right spot, right? If I put some other number here, the line's not going to be in the right spot. Yeah, see, in CO2, right, we'd be dead. Yeah, because CO2, you got to have some of that. That's very important, but if you have too much, that's a problem. And you can't have negative, right? You could have 0, but that's probably not possible. The Earth would not be livable. I guess it's possible, but we wouldn't be able to live here. All right, so again, in this case, I don't have a reasonable interpretation. Sometimes you do, so I'm just going to tweak this a little bit to give an example of when we might have a reasonable interpretation. Let's make a copy of this, duplicates. And what I'm going to do is just get rid of some stuff here, get rid of that stuff there, go away, and I'm just going to slide this over, and I'm going to introduce a new variable. I'm going to call it T. And what I want T to be is years after 1960. Right. So then this right here would be year 0, and this would be 5 years later, and so on. So I'm going to actually calculate that. Take the given year minus 1960. So a lot of times we'll do this when we have a year involved, because it's easier to talk about years after some point than to use the actual year. Next thing I want to do is I'm just going to recalculate the slope and the y-intercept. So these ones right here were based on the actual year. So I'm going to recalculate them based on this new variable t. And what you should see is they're not going to change. So here I want to do the correlation. Well, some of them aren't going to change. And then I want the y data, comma, my new x data, parentheses. I'm just going to copy these guys here to make it easier. Control and not silence, sorry. So I get the same correlation coefficient. I don't want to fill that down, that'll screw up. And then I want the slope. You'll see when I paste that in, I get the same slope. Y-intercept though, because I changed what x meant, that's going to change. So this time, intercept data. All right, I got a totally different number here. What does that y-intercept mean if I were to look at this? So let's, if we graph this, it's going to look just like the other graph, except it's different numbers on the bottom. I'll start up higher. Let's go to series. Nope. Vertical axis. Maybe start at 300. Start. Yeah, that's about right. There's the same set of points I had before. I just changed what I'm calling the numbers at the bottom. So what is year 0 here? Well, year 0 is really 1960. So because I have this new variable, t years after 1960, when I think about what this number right here, the 311 means, so new page. So instead, I have this new variable t, where this is 0, and that's 10 years later after 1960, and 20, and 30, and 40, and 50, and so on. No, it wouldn't. So often we might do two things. We might just say this is just years after. So instead of having these numbers here, we would just have these other ones with a label that says years after 1960. But we could totally put the 1960 in. If, however, the 1960 is here, and that's 1970, and that's 1980, this has to be up here. This has to be the y-intercept. However, if I get rid of those years, then the y-intercept is no longer that, it's 311. And if somebody says, oh, what does the point 0, 311 mean? Well, this interpretation is really the year 1960, and this is the parts per million of CO2. So now I can say, oh, well, this means in 1960, we think the parts per million of CO2 is about 311. So now it actually has meaning. So sometimes the y-intercept is meaningful, sometimes it's not, but we need it no matter what. What's more important though? The slope is the more important one. That always has a meaning if you have a linear trend. It has a meaning. If you don't have a linear trend, then we shouldn't have had a line in the first place. Okay, so those I think are all the big ideas from section 2.5 and section 2.6. I'm just going to put up a couple more tips and things to think about. Page, please. So just kind of about correlation and predictions. There are definitely, you can't just run numbers and say, here are the numbers, right? You got to think about them. And again, when we think about them, the first thing we have to do is look at the scatter plots to see if there is a linear relationship. If our human eyes don't see it, then there's no point in proceeding. 2, are there any significant outliers? That sometimes is a judgment call. There are ways to calculate that. We talked about some of them last time. And then if there are, what do we do about them? Do we pull them out to see if there's a difference, or do we leave them in there? 3, is there a significant correlation? And significant is undefined at the moment. We're just going to use significant as close to 1 or -1. Now, some other considerations. So we've talked about these last time and this time. Those are the main 3 things you think about when you're making a linear model. So some other important things. Just because there is a strong correlation doesn't mean there's a reason for it. So high correlation does not mean there's some cause and effect going on. That's a whole nother area of study, and you got to look at other variables and see if there might be any confounding variables going on, or if this is just some weird coincidence. So confounding variables have to be considered. So those are just other variables that are related that aren't currently being looked at. And that last example in section 2.7 is really great, an example of confounding variables. So maybe there's some confounding variables, and it could just be a coincidence. Like last week, or last class, I talked about the amount of chicken people can consume per year versus the number of, let's see, rain in Montana. Right? There's no connection between the amount of chicken we consume and the amount of rain that occurs in Montana. Another crazy example I had was motorcycle deaths versus sour cream consumption. Right? There was a high correlation, like 0.9, but that's nonsense, right? There's nothing there. So just because we have a high correlation doesn't mean there's cause and effect. That has to be thought about further, and confounding variables need to be considered. Another consideration, if there is a weak correlation, does not mean there's no association between the variables. It could be that there's some other kind of relationship, like maybe a curve, like an exponential model, not a line. The correlation that we calculate here is only to see if the points kind of line up. There could be a relationship, but it's not a line. Okay, so that's another important thing to think about. And then even with the high correlation, you could have a high correlation, but it shouldn't be a line. So yeah, correlation is just one of our tools to look at this, but there are many others, and this course is just scratching the surface on that idea, because there's many kinds of relationships between variables. There's wavy ones, and U-shaped ones, and hockey stick-shaped ones, and just there's tons of them out there. So those are some of the big things to be concerned about. Just because we have a high correlation doesn't mean there's cause and effect. Just because there's a high correlation doesn't mean it's linear. And if there's a weak correlation, that doesn't mean there's no association. There could be some other kind of association that's just not linear. At the moment, we're just focusing on linear stuff. All right, so that is a long video.